continue our paper. So this is the final part, and so yeah, I preloaded some of the questions, and some of the questions we're just going to work through together. So the first part, it says, let me get a very good, yeah, this is good enough. So let's use this. And the question 11a, it says the mass of potassium is 39 and the proton number is 19. State the number of electrons of the potassium atom. Okay, so state the number of electrons. So state the number of electrons of the potassium, and it says atom here. Okay, so atom, it means it's neutral. For an atom, the number of protons. Okay, this is number of protons equals number of electrons. Okay, so for a neutral atom, it means that the positives, which are the protons for our case, they're equal to the negatives, which are electrons in our case. Okay, so if you're asked to find to state the number of electrons of a neutral atom, it's simply equal to the proton number of that atom. So you just we are given that it's 19 here, so the number of electrons is 19. Okay, so it's 19. Then it says determine the number of neutrons of in the potassium atom. Okay, so number of neutrons equals mass number. Mass number is also nuclear number. Okay, minus proton number. So this is the formula. So a mass number, it's always the largest number, or not always, but then the largest number in an atom, it's almost always the mass number. So in our case, it's 39. I'm just telling you one way you can easily tell apart the numbers. So the proton number for our case, it's 19. So 39 minus 19, what do you get? You get 20. Okay, so the number of neutrons, it's equal to 20. Neutrons, they are neutral. They are the prefix here, neutron. It's also associated with the word neutral. Okay, it doesn't have any charge. It's neither positive nor negative. And then the proton, you can take this P here as positive. Protons are positively charged, and electrons, they are negatively charged. Okay, let's move to the next part. Next part says potassium reacts with fluorine by donating electrons. Okay, so donating electrons. State the number of electrons donated by potassium and the charge of the potassium ion. So I understand that you're given, you're asked to find the number, to state the number of electrons donated. Okay, metals tend to donate electrons, non-metals tend to accept electrons. So we have potassium here, which is a metal, and we have fluorine, which is a non-metal. So potassium will donate electrons to fluorine, okay, such that both of them, they both achieve what's called octet state. So for example, hydrogen needs 2. So the first electron shell, it only needs 2 it only needs 2 electrons to be stable, and then the next one, you'll be filling it up with 8, and then successively you'll be filling up with 8, like that. So there are 2 ways by which you can find the number of electrons donated. For 19, it would be 2, 8. The electron configuration would be 2, 8, which is 10, plus this, then you'd have 1. Okay, so this would be the electron configuration, at least in terms of numbers. So if you're asked to find the number of electrons donated, it would donate this one here. Okay, so it would be 1. So it would donate this one, just because it's when it donates this one, then the outermost shell is actually filled up, thereby it's stable. And then fluorine accepts this one as well. So the charge on the potassium ion was neutral. The potassium atom was neutral, and then it lost an an electron, so it lost one negative. So now we have positive 1. If you're having a hard time understanding this, you can say if atoms donate electrons, so which for our cases, metals, when metals donate electrons, they become positively charged ions called cations, okay? And when fluorine and other nonmetals accept electrons, they become what we call anions. Okay, so cations positive, anions negative. Okay, so this one was a metal, so obviously it'd be positive. The number of electrons lost. So write the formula for potassium chloride. So here, just write the symbols first. So potassium, then okay, it's actually fluoride. So potassium, then Kf like this. Then, in principle, what happens is you take the valence. The valence is the number of electrons that an atom wants to complete its octet for nonmetals. So for this fluorine, it's actually in group 7 in the periodic table. So it wants one electron only. So we say that the valence of fluorine it's 1, and the valence of potassium it's 1 as well. The number of electrons needed to achieve octet. For metals it's losing, for nonmetals it's gaining. So this one would be in group 7, so it would need only 1. So this one valence 1, this one valence 1, and then thereby they switch. This one would be 1, this one would be 1. That's why I'm writing only Kf here. Just an illustration, let's say we have we need to find for sodium oxide, so it would be sodium here, then oxygen here. Then sodium is in group 1 of metals, so the valence would be 1, so you'd be putting 1 here. Oxygen is in the group 6 of elements, so the group 6 elements they need a total of 2 electrons to fill up, so the valence is kind of the number of electrons required, it's 2, so here it'd be sodium oxide like this. So yeah, so you just switch, take the valencies, then you switch them. The number of for metals, we're concentrating on the number of electrons lost. For non-metals, we're concentrating on the number of electrons gained in order for these two elements, these two atoms to achieve octet state. So the formula would be this one. State any one physical property of potassium fluoride. So here you just have to identify that this is a ionic compound. Okay, once you identify ionic compound, it means that there is no sharing. One of the elements is very electronegative than the other one, so it means that there is complete transfer of electrons from the metal to the non-metal. Okay, so here there are ionic compounds. If you have ionic compounds, you can actually generalize the physical properties. For example, you can say high boiling points. Okay, you can also say that it's crystalline in structure, I'm sure, and it's white. It's a white powder, sort of. It's made up of white crystals. So here, the physical properties. Remember, these are things that have to do with the physical attributes. So you're not concerning yourself with transfer of electrons or the chemistry of the compound. You're only concentrating on the physical aspects. So for example, boiling is not a chemical change. That's why we say high boiling points is a physical property. So let's move over to the next part. So let's continue with our part C. It says sodium hydroxide. So this is the formula. Is dissolved in water to form a solution of concentrated of concentration thus. Okay, so if you're doing chemistry, dm cubed is simply liter. Okay, so it simply means 0.5 moles per dm cubed, so per liter, so it'd be molarity. There's no difference. And then calculate the number of moles of sodium hydroxide of the solution. Okay, so we are given, this is how I would write it. Okay, I'm just collecting the information here. Concentration equals Okay, you can even note so that we don't include equal signs too much. So C equal to 0.5 moles per dm cubed. Okay, so and then volume we're given as well. So volume equals 250 cubic centimeters. But then in order for you to actually play around with the concentration, the volume, you have to match the units. So here we're given moles per dm cubed. We have to convert to dm cubed for this one as well. So the conversion is 1 dm cubed equal to 1000 cubic centimeters, like this. This is called the conversion factor. Okay, so here just treat it as if it's liter. That's the hint. Okay, dm cubed, it's simply liter. So here this ones will cancel, and then you'd get 0.225. Okay, so 0.25 what? dm cubed. Okay, so number of moles N equal to concentration by volume. Okay, so 0.5 here would be mole per dm cubed multiplied by 0.25 dm cubed. Okay, so those ones will cancel. Here you get 0.125 moles. Okay, so you get 0.125. You can also say 0.5 multiplied by this, it means half of this. So half of this is 0.125. And that's how we get this one. So let's quickly move to the next part. So the table shows the number of bubbles produced when metals A, B, C, and D reacted with dilute sulfuric acid for 3 minutes. Okay, so we are dealing with the reaction between a metal and dilute sulfuric acid. Okay, these are the most important details in the question. Okay, so name the gas produced when a metal reacts with dilute sulfuric acid. The gas produced is hydrogen. Okay, whenever you have a metal reacting with dilute sulfuric acid, hydrogen is produced. Then the next part says identify with the reason. Identify with the reason the most reactive metal. Let's see. Yeah. So here I already preloaded the answer. Yeah, the most reactive metal, it's D here. Why? Because it produces the highest number of bubbles. Okay, after the 3 minutes. So it produces the most hydrogen, in other words. So that's why we chose this. So yeah, again, a metal reacting with sulfuric acid produces hydrogen. It's just like that. Let's quickly move to the next part. Next part says state any one alloy of copper. Okay, so I actually preloaded this question. I actually preloaded this whole question here. So the state any one alloy of copper. Okay, so you have brass and bronze. These are the two most popular alloys of copper. Okay, for brass we have copper and zinc. So just remember that sometimes they ask you. So for bronze it's copper and tin. Okay, so copper and tin, copper and zinc. That's it. So you're supposed to just state one there. So the metal used for galvanizing iron, it's zinc. Okay, so galvanizing, it simply means putting in a protective coat, okay, or a protective layer. So that protective layer for iron, we put a more reactive metal. So it's usually zinc. Okay, so yeah, the metal used, it's zinc. Define a compound. So a compound, I'm just going to discuss some of the elements that I've included in this definition. So a compound, it's a chemical species comprising at least two different elements chemically bonded together. Okay, So there is some chemical bond that will be happening in the compound. Okay, so and then there are at least two different elements. If it's let's say hydrogen gas, it's not a compound, although these two, they are chemically bonded. They are actually the same element. Okay, so they have to be different elements. So for example, sodium chloride. Okay, so this is an example of a compound. It's got two, it satisfies those two different elements, sodium and chlorine, and they're chemically bonded together. This is ionic bonding between these two. So the any chemical species comprising at least two different elements chemically bonded together, that's a compound. Okay, and then this is a molecule. And this one we call it a compound, and we also call it the formula. We also say that this is a formula as opposed to this molecule. So let's move to next part. Explain why copper does not react with zinc oxide. Okay, so copper is less reactive than zinc. So the reactivity says, I don't know you guys the mnemonic that you use, but then for us it was polite, spotted, which is means for sodium, polite, spotted, leopard, which is for is it lithium, I think. Polite spotted leopard can meet calcium, affectionate zebra, aluminum, zebra, zinc, into highly tender loving care than iron, and all that. So it's called a mnemonic phrase. Find one mnemonic phrase that you can use so that you remember the reactivity series, because it's very popular in your exam. So polite spotted leopard can meet affectionate zebra into highly tender loving care. Single girls, please. It includes all the elements there. Okay, so I'll try and do an extra video some other time, so that I'll be just explaining the reactivity series. But then what it is that it gives you an idea of what element can displace another. So here, if you have copper and you have zinc oxide, you want the copper to displace zinc, so that would have copper oxide and zinc. And this can only happen if copper is more reactive than zinc. So the reason it's not happening, the reason there is no reaction, is that copper is less reactive than zinc. As such, copper does not displace zinc in zinc oxide. If it were copper oxide and zinc, copper would be displaced just because zinc is more reactive. Okay, let's quickly move to the next part. Next part says fig this. It shows a pulley system used to lift a load of 600 newtons. The efficiency of the system is 75%. So you're given the efficiency. The efficiency, it simply means the ratio of the output, work output, to the work input. So we're given is 75%. Then you're asked to define the term machine. Okay, so define the term machine. So a machine is any tool that multiplies the human effort, or that gives a mechanical advantage. Okay, so this is and then another definition would be any machine. A machine is any device that does a specific task. So any device that does a specific task, it's called a machine. Okay, so yeah, that's it. So what's happening here is you're pulling here the effort. The system is 75% efficient, just like what we highlighted. So normally, if the system were 100% efficient, would be having a mechanical advantage of 2. That means that the effort here would be only 300. It would be half of this. Okay, so the mechanical advantage would be the number of pulleys. There's pulleys here, of which is S2. The problem now is that this pulley system is actually just 75% efficient. So it means that there is some work which is done against our frictional force. So to get that the actual effort, so actual effort is equal to, so actual effort usually we say and a number of pulleys. Let's say here you'll be dragging it by this length and then also this length, so it'd be like half always. So if it were 100% efficient, the effort would be 300 here. Get it? So it'd be 300, the tension here would be 300, the tension here would be 300, such that it'd be supporting this 600 Newton force. So you only have to apply 300. But then the actual effort is actually equal to 300 divided by Newtons divided by 0.75, which is the efficiency. Okay, so you say 300 Newtons divided by the effort. So 300 divided by 0.75, so you actually get 400. Okay, 400 Newtons. So just to recap, what we did here is this is 600. We have a mechanical advantage of 2, so the tension here would be the same. So the tension we expected to be 300, but it's not actually 300 because it's we have this factor here, which is the efficiency. So we have to divide by the efficiency to find the actual effort. So the actual effort is 400. Okay, so mechanical advantage equal to load over effort, which is equal to, the load is what? The load is 600. Okay, over the effort is what? The effort is 400. Okay, so here we'd get here would be 2, here would be 3. So the actual mechanical advantage would be 1,5. Okay, so 1,5 would be the actual mechanical advantage. So normally for these pulleys, if it's 100% efficient, we say we count the number of pulleys here. But then the problem now was that it was only 75% efficient. That means that we are doing some work against some work against our frictional forces. So we had to find the actual effort. We had say that this would be 300 normally. So for the output, desirable output, 400% efficiency, it'd be 300. But then this is only 0.75, which is 75% here. So the actual effort is 400 Newtons. So 400 Newtons is the effort, and you have the load, it's 600. So the mechanical advantage is 1.5. Let's move over to the next part. Next part says electrical appliances have a metal casing. Okay, electrical appliances which have a metal casing are usually fitted with an earth wire. Explain how an earth wire acts as a safety device. Okay, so electrical appliances which have a metal casing are usually fitted with an earth wire. Explain how an earth wire acts as a safety device. So here I preloaded the answers already. So let me just unload them, and then we discuss some of those things. So in case of a short circuit, this is important. Okay, what electrocutes people? You have a short circuit, so it means that a part of the electrical system which is not supposed to be in contact with the metal casing, it's now in contact with the metal casing, and thereby you can get electrocuted. So if an earth wire is fitted now, the earth wire provides a zero resistance path. So you may have heard that electricity, it allows the path of least resistance. Okay, so for earth, if we connect an earth wire to the ground, if you can connect any wire to the ground, the resistance there, it's zero. It's a zero resistance path. So the electric current would flow to the earth. It would flow to the earth wire here to the ground. So in case of a short circuit, the earth wire provides a zero resistance path for the fault current to follow to the earth. Okay, so this way the current chooses against the path of the operator, thereby avoiding electrocution. Okay, so you avoid electrocution. Basically, the electric current has two pathways. It can go through the person or the operator here, or it can go through the earth. So the reason it goes to the earth is that the earth, it has zero resistance. Okay, it has zero resistance, so it goes there instead, and then thereby the operator avoids electrocution. So yeah, that's it. And then here it says define the term mass. So mass it's a measure of the inertia of an object. This is the physics definition. Okay, this is important. Inertia, it simply means the unwillingness to change state, and this state can be in two ways. It can be a state of rest or a state of uniform motion. Okay, uniform motion in a straight line. So objects, they have a tendency to resist a change in motion. If it's at rest, it wants to remain at rest. If it's moving in at a steady speed, it wants to remain that way. So the inertia of an object, that means the unwillingness to change its state, it's a measure of the mass. Okay, the mass is what determines how an object accelerates, how an object changes its state after it's moving. So yeah, so this is the physics definition, but you can also write the amount of matter in an object. Okay, the amount of matter in an object, it's also accepted, but then it's more of a very watered down definition. This is the proper definition. If you can commit to memory, then you want to have this very much. And so they define the term weight. So the weight of an object, it's the force that acts on a body due to gravity. Okay, if you place an object in a gravitational field, the object tends to accelerate towards the ground. So we can deduce that the object has a force in that direction. Whenever we find a force, whenever we find an acceleration, we find a force. There is definitely a force that accompanies acceleration. So when the force that acts on a body due to gravity, it's the weight of that body. Okay, or the force that acts on a body placed in a gravitational field. So the same thing. We don't see gravitational fields; they are just a phenomenon. Sometimes we represent them by these imaginary lines called field lines, but then we don't actually see them. But if a thin thing is placed near the Earth's surface, it's actually subject to that gravitational field. Okay, so and then the third part says define momentum. Momentum is the mass velocity product of an object. This is important in analyzing how an object collides with another object. So if a collision is not only dependent on the mass, massive objects can have very small effect in terms of collision, and also small objects can have a very huge impact in terms of their impact. Their in a collision. A collision is any event where the mass velocity product changes. Okay, so you can look at a bullet; it's very small, but then the velocity would be like very large. So at the end of the day, you actually have a massive impact. So that's the concept of momentum. It just gives a nod to say it's not only the mass, it's also the velocity. Not only the velocity, it's also the mass. So it's the mass velocity product of an object. That's the measure of momentum. Okay. So let's move to the next part. Next part says this fig, it shows how the length of a glass rod is measured. Okay, so we're measuring using this. Name the instrument. So the instrument is called a vernier calipers. Okay, so vernier calipers, and you're asked in the next part. You're asked what's the reading, what's the scale reading. So yeah, this is the beauty of those questions. I get to explain to you something that would be hard to explain in a classroom setting. So you see, you just follow my cursor. This you have to read the main scale. The main scale is this part here. Okay, so this is the main scale. You have to read it, and what you're looking for there is you're looking for the part just before this small scale. you know, slides in. So it would be this reading here. So this reading here, that's what you're looking for. For the main scale, this reading is 1.3. Okay, so it'd be 1.3 for the main scale here. Then you also have to find the reading for the small scale. Okay, so you can see here it's kind of in the middle. To find the exact value, you actually have to find where these scales, these two scales coincide. Okay, so it's hard to tell here, just because it's a duplicate of a duplicate. But where they are closely aligned, it's actually at this 5 here. So it'd be 1, 3, 5. Do you get it? So what we did was main scale. This at the bottom is that's the main scale, and then it's measured in millimeters. So here this is 1 millimeter. Then this is 1.1.2.3. So it'd be 1.3 millimeters so far. And then we have to find where this upper scale, this small scale, it coincides with this other scale. So they coincide here on 5. So it'd be 1.35 millimeters. Okay. Let's quickly move to, yeah, I think we stated it already. Let's see how it preloaded some of the questions. So here we had said 1.35. If you still remember, it wasn't really clear, so you might see it coinciding somewhere else, not the 3.5. It would still be okay. You just make sure that you write properly. Okay. So state Newton's third law of motion. It says every action has an equal and opposite reaction. Okay. So this is the poetic way to say it, but essentially it says every action is accompanied by an equal and opposite reaction. Okay. So explain what happens when a person sits on a chair in terms of Newton's third law of motion. So the weight of a person acts in the downward direction. So here you have to understand the context. They're asking you on Newton's third law here. They want you to apply it appropriately. Okay. So the weight of a person acts in the downward direction. So that's what we know. And then the reaction force equal in size. The reaction force equal in size to the force. Okay. So I'm gonna put some commas here. Acts in the upward direction. So you have your person here. Okay, so this is a chair here. So this is your person. Let's say this is the ground. Okay. So the person here, there is a force mg acting in this direction here, and then there is another force equal and opposite, which is called the normal reaction. It acts perpendicularly to the ground. How do we know that this force exists? Because this person is not moving. Anything that does not move, or anything that moves at a steady state, it means that the forces involved on that object, they are in balance. They are in a state of balance. So this one, the downward force is balanced by the upward force. The upward force is called the normal reaction. Okay, so reaction force equal in size to the weight. So you can say to the weight acts in the upward direction. So here, if you want, you can even scribble, you can even draw this little diagram here. Then that's it. A force of 300 newtons pulls on an object of mass 60 kgs along a horizontal surface. Okay, calculate the acceleration. So acceleration is equal to, so most people, they remember force is equal to mass times acceleration. Okay, force is equal to the product of mass and acceleration. So acceleration is equal to, by change of subjects, is equal to f over m. Okay, so let me not put double equal signs. So here we have 300 newtons divided by 60 kgs. These are standard units, so we are very happy about this, because here we have to use standard units so that we can get our answer in standard units as well. So the standard units for acceleration, it's meters per second squared. So in our case, it's 5 meters per second squared. Okay, so that's it. Acceleration equals to force divided by the mass, and that's it. So let's move to the next part. Next part says this is a circuit used to determine the resistance of a wire. Okay, so this is the wire. Yeah, this is the wire. And then you're asked, do you name instrument Y? Instrument Y is obviously a voltmeter. How do you know? Because it's connected in parallel. Okay, a voltmeter. Some say voltmeter. Okay, parallel connection. And in case you don't know what parallel connection means, it means see here, this is the directional flow of current. If you connect anything like this in this way, it's called a parallel connection, as opposed to connecting something in series. So this ammeter here is connected in series with a supply battery. So that's it. So voltmeter, parallel connection here. So it's connected in parallel. Okay, that's how we knew that it was a voltmeter. And also to measure resistance, you require, this is called Ohm's law. So Ohm's law says V is equal to IR. So these are elements of Ohm's law. So V is provided by the EMF. EMF means all the electromotive force here, or you can say EMF is the voltage. Okay, the voltage is provided by the battery here, and then the current is provided by the ammeter here, and then the resistance is the what we are measuring. So here R would be equal to V over I for our case if we change subject. So if we keep on getting corresponding values for V and for I, then we can actually find the resistance from that calculation, and then it will always be the same for ohmic conductors. Okay, so state the effect of using longer wire of the same thickness and material. So I preloaded this. So the resistance of the wire increases. This is what they would have just wanted because it's just 1 mark. Okay, but then it increases in a way that is directly proportional to the length. So I'll give you a case practice where some of those things are applied. So when you see overhead wires, they're actually the same material and the same thickness for the most part. And the reason for this is that they have what they call per unit resistance. So this per unit resistance concept now is if you're given any, you would know the per unit resistance, and if you're given any length, let's say you're given, oh, your conductor is actually 2 kilometers, then you can just use the per unit resistance with in simple proportion with the length that you have, and then you get the exact resistance that you want. So this is because if you're doing if you're doing physics, then you probably know this. Okay, so this is the resistance here. This is the formula for resistance. So resistance equal to, this one will be length of wire. So even if you're not doing sciences, core sciences, just remember that resistance is directly proportional to the length of the wire. The longer the wire, the larger the resistance. Okay, so that's why we say increases. This one is the area. So here, if the area increases, it means that the resistance goes down. Thick wires, they have lower resistance than thinner wires of the same material. Okay, this is called the coefficient of resistivity, and resistivity coefficient, it's unique to every material. So for copper, you'd have depending on the actual material, you'd actually have the resistivity values there, and for aluminum, it's also the same thing, on and on and on. So you just knowing the formulas, it helps you unpack some of those questions. So the resistance increases, you can stop at this, but then you can also say it increases in a way that is directly proportional with the length, and then that's it. Let's move to the next part. So next part, question 15, that will be our last question. It says, name any 3 types of media for signal transmission. So I had to actually load this. So there is a coaxial cable, there is optical fiber, there is radio waves. Okay, so these are all media. If they had said two, you would have said guided and unguided. Unguided would be wireless, and unguided would be this stuff. So coaxial cable, it's coaxial. It means it's going in two axes. Same as the um, one we use for uh, DSTV. So if you actually analyze the cable that leads to your decoder, it will be coaxial. There'll be two separated insulated lines or insulated cables that will be there. They're there, and then it's called coaxial cable. So TV stations mostly. Optical fiber, it's we use we'll be describing one of them here, so we'll be describing optical fiber. So won't go there. But then radio waves, it's also a mode of transmission. So we also use radio waves to transmit signals. So it's also a medium. Describe how signals are transmitted in any one of the medium named in one. So we named optical fiber medium. So it uses light. Light simply means electromagnetic waves. Okay, visible and invisible light. So yeah. So there's some part of light that we don't see. So it's called the invisible spectrum, and the part of that we see is called the visible spectrum. So optical fiber technology, it actually uses light to transmit signals. Okay, so digital signals, you use light, and the advantage is that it's super fast. And when designed very well, it's also the signal it's very strong as well. So the principle of operation is total internal reflection of light. Okay, so you'll be having this cable here, and the light waves will be bouncing in between, and such that you want very much for the signal to be lossless. So it means that if it bounces, then it's supposed to have that mirror effect, as if you're bouncing a basketball to the wall, so that it comes back on and it goes back again and all that. So here we say that this principle is called total internal reflection. It means we are reflecting all the light here, such that when it reaches the other end, because optical fibers they also cover a significant distance in some cases. So you want that signal to get through as strong as possible to the source. Okay, so yeah. So that's it. So media of signal transmission, by the way, it simply means what is it exactly that you're using to transmit a signal from the source to the recipient. Okay. So the function of the decoder. Oh, this is interesting. So the function of the decoder, it's actually what we were discussing just now. And then let's see. So yeah. So it's a circuit that changes received code into the desired output signal. Okay, so it means decode. So the signals being sent, they're coded in some way. So here these electromagnetic waves. When they reach the other side, you want to receive them as something specific. Maybe you want to receive them as a picture, as an image someone is sending you, or you want to receive them as a video. So you need a decoder to do that. It's like a medium. It kind of checks that signal, it processes it processes it in such a way that you can get a desired output. And that's it. So describe 3 advantages of email over ordinary mail. Okay, so I preloaded this. So the one advantage is instant delivery. You can send someone in UK a message right now, they'll be able to see it instantly. If you send over ordinary mail, you have to wait sometimes maybe up to 2 weeks or something like that, so that they'll come pick it up maybe from your post office, drive it to some sorting center. Sorting center takes that to the airport. The airport authorities take that to the other country. The other country, it takes the mail to the sorting center again. Sorting center again, they distribute to local post office, and then afterwards the postman comes and then gives you a package. So you can see how ordinary mail is kind of disadvantageous in that way. You have instant delivery, you just send an email, boom, it's just there. And generally emails are more secure, so like there's no interception. So especially with some encryption technologies that are there, there's what we call end-to-end encryption. So sometimes, depending on what email you're using, they actually build infrastructure, electronic infrastructure, such that your email will be secure. It's really hard to hack without knowing the person's password, sort of. But then over ordinary mail, someone can just open it up. It just doesn't happen that much, but then yeah, it's also something. So it's environmentally friendlier. So this one was kind of posh, but then I wanted to include it. If you this would assume that ordinary mail is carrying a message, so you actually have to write it on paper. That means that you're burning, you're destroying some trees somewhere so that you could make that paper. So a more environmentally friendlier way would be to actually just send an email. It does the same thing without having to use paper. So using paper, it's sort of like disadvantageous in terms of our environment. Okay, so and then it's not limited by distance as well. This is what we covered, that it's instant delivery. So yeah, that's it for this paper. These days I've been yesterday we uploaded video. Today this is another video. So I'll try to do at least something every day. Thanks so much for watching. You've been kind watching the videos. I really wish you well in your exams. Just do your best, and just follow through. If there is anything that you didn't understand, the comment section is there for you, and we'll be able to respond to you promptly. And yeah, so we're also working on some things that we want you to get onto. We'll be informing you later, probably early next month. But then we are very excited about some of the packages that we are preparing for you. So yeah, that's it from you, Yubo, out.